Okay, so this is what's given. Change the color, M1 and V1 original, right? And M2 and V2, your physics teacher uses not the 0 instead of I, right? Okay. And then you have to find V1 final and V2 final. So what you want is V1 final and V2 final. I know the subscripts kill you in physics, especially in momentum, right? Here's our problem. M1 V1 original plus M2 V2 original is equal to, momentum is conserved. So conservation of momentum gives you this much, right? Here's our problem. We have two unknowns, right? V1 final and V2 final, and we only have one equation. Boy, right? Actually, I want to write the title of this statement. This is conservation of momentum. Momentum is always conserved within the system. You know what I'm saying? Without any external force. See, that's why they usually give you one of the two, right? One of the final velocity, then you can calculate whatever is remaining, which is an easy algebra. Or they make it perfectly inelastic, so these two are same, right? They're stuck together. Then there's just only one variable. In this case, we have two different variables. How are you going to find it? We need one more equation. Where's that one more equation come from? That comes from this word elastic. What's the definition of elastic collision? This means energy is conserved as well. That's what elastic is. If you bounce the ball off the floor, then it bounces up to exactly same height. Of course, there's no perfectly elastic collision, but we can come very close. Billiard balls, they are almost elastic. You know what I'm saying? So we have this conservation of energy, kinetic energy in this case, right? Kinetic, just write energy, because there's no potential energy here. Good. Let's see what that gives us. That is 1/2 M1 V1 original square plus 1/2 M2 V2 original square has to be whatever the energy is transferred to the final state. This must be true. So this gives us systems of equation. Except this is a horrible systems of equation. How do you solve such a thing, right? So this requires a unique trick, and here's the trick. Number one, I'm gonna multiply both sides by 2 and collect the like terms according to m. So I'm gonna have m1 on the left-hand side. Like that. Too much algebra? And m2 is on the right-hand side. Too much algebra? Ne? I'm going to do the same thing over here on the momentum equation. So m1, v1 original minus v1 final is equal to m2, v2 final minus v2 original. Good. I'm going to call this equation 1, and I'm going to call this one equation 2. And I'm going to vertically divide the 2. So here comes 2 divided by 1 equation. You can vertically divide the equations, right? Beautifully, m cancels, you get v1 original plus v2 v1 final is equal to switch them, that's because it's plus. So V2 original plus V2 final is what you get. Good? I'm going to call this equation 3. And our task now becomes systems of equation between this and this original momentum equation, which is infinitely easier system to solve because this is linear now. You get it? You solve it for one of the two and plug it in, and then you can solve. You want me to do it? Yeah, sure. Which one do you want me to eliminate? V2 original, V2 final or V1 final? Your choice. Fine, V1 final. V1 final is equal to V2 original plus V2 final minus V1 original, isn't it? And then we substitute it into this equation. And with the computer, it's easy enough to do. Substitute. Good. You with me? Okay, so when you make that substitution, what happens here is M1 V1 or original plus, and this is V2 V1, we are keeping it, M1 M2 V2 original is equal to M1, and then we are eliminating this one, right? So substitute this thingy in. V2 original plus V2 final minus V1 original plus M2 V2 final. Good. You see we can calculate V2 final now? Say yes. So M1 V1 plus M2 V2 is equal to M1 V2 original plus M1 V2 final minus M1 V1 original plus M2 V2 final. Good. And then, like terms, what we want is this term and this term, isn't it? So V2 final to the is equal to, move everything to the other side, so M1, you see you have two of M1 V1 original between this thingy and this thingy, minus M1 V2 original over M1 plus M2. You get it? And then if you want V1 final, you just plug it into this thingy. You know what I'm saying? So I just make a copy. If OneNote does not want to copy anymore. How about that? Thing, huh? This ugly expression goes in here, and then that gives you. Well, numerically, because usually the numbers are given, so numerically, once you have that, you plug in the numerical value. You know what I'm saying? Not that you're going to memorize it as a formula. Should we take an example? Yeah. Say there is, I think you have seen this kind of thing. And then I want to place M1 here and M2 here. And then let's say M2 is so much bigger than M1. Okay? And then this thing has this height h. When you drop it, and let's say this is frictionless plane, and this is stationary, so V2 original is 0. Then it glides, let's say, elastically, and then how far does it move back up? This will move to the right, and this will bounce and then back up, right? How far does it move in comparison to h? You want to have numbers or not? Say this is 10 meters. To have it realistic, I'll still work without the numbers, but this, let's say, is 1 kilogram. And let's say this is huge, 10 kilograms. Okay, this is a setting. Shall we start? Okay, so what we have is M1. Oh, first we have to calculate the V right before the collision, right? That we are going to use conservation of energy. So 1/2 M1 V1 original. V1 original is right before the collision because it really starts with 0. Square is equal to mgh. M1gh. M's cancel, so V1 original is equal to square root of gh. You know what I'm saying? Say yes. Say yes. Huh? 2, oh my God, 2gh. Okay, whatever that is numerically, you calculate it. Now, once you know that, then our next task is M1 V1 original plus M2 V2 original is equal to M1 V1 final plus M2 V2 final. You know what I'm saying? Now let's simplify this thing a little bit. This thingy is 0, isn't it? So our life is slightly easier. And then this thingy is this expression right there. Okay? See, in physics, if you keep everything in terms of variable, it doesn't matter which one you do first. You could have done this first, right? And then let's go back. Instead of rederiving it, we're using this expression. You know what I'm saying? Question? Mm-hmm. Right, M2 V2 original is not here. Excellent catch. Oops. Oh, you just saved the day. Plus M2 V2 original. Okay, in red, so that's the one that I neglected. Okay, and then everything else stays the same. But it's like, I never use this anyway. I'll use that thing. So come here. Good. So it's like, it's kind of rings of, I mean, it's handy to remember. You know what I'm saying? And then we are going to eliminate V2 final this time because we want this V1 final. You know what I'm saying? So from here, we get V2 final is equal to V1 original plus V1 final, and then minus V2 original. Good? And plug that in to our momentum, this thingy. So now we have M1 V1 original is equal to M1 V1 final plus M V1 original plus M1 V1 final minus M. I think I messed up the subscript, right? This is M2. Good. M2 and then V2 original. So far, so good. And we are solving for this guy and this guy. You get it? So we have V1 final is equal to M1 V1 original and minus plus M2 V2 original minus M2 V1 original. Good. Over M1 plus M2. Good. Did I miss anything? I think I got everything. And then numerically plug in these numbers that we have here, and then you get the numerical value. Do you see this will be a negative number? Because this M2 is big compared to M1, and V1 original is something, you know what I'm saying? V2 original is equal to 0. This is 0. You know what I'm saying? So do you see that this is a negative number, telling you it's bouncing back and moving back up now? Good? Good, 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 good. I don't want to plug in the numbers, but it's there. Now, finally, we have to calculate how far it moves back up, right? So we use conservation of energy again. So what we have is, finally, 1/2 M1 final square, 1/2 M1 subscripts kill us. V1 final square is equal to M1 G H2. Let's call it H2, the height that it moves back up. So H2 is whatever this height that it'll move back up. And M's once again cancel out, so H2 is equal to 1/2 M1 V1 final square all divided by 2. So let's just write it. I mean, all divided by G. How's that? Did I miss anything again?
Why is the M still there? It's like
Oh my God. There, it's really not. Good. M's cancel. So this is your final answer. So numerically, let's walk this through. You compartmentalize this problem. Part A, you figure out the velocity of this block right before the collision using conservation of energy. Now you use a conservation of momentum and elastic thingy to solve for the final velocity of the block that you want. Then that problem is over. You get a numerical answer. Then you use conservation of energy again to compute the height. Of course, if you want to know how fast this thing is moving, you plug it back into our thingy right here, this thingy. You know what I'm saying? Once again, this V2 final is 0, so it's like something to keep in mind. Good.